How to design a logarithmic amplifier circuit is discussed in the circuit design example. This is implemented with two operational amplifiers, or op-amps, a pair of matched bipolar junction transistors, or BJT, in the same package, and we have a number of passive elements like resistor and capacitors. At the input of the circuit, at one input, we have a 10-volt reference voltage. That's an internal input. The main input is Vn, which is a positive voltage that has a value between 0 and 10 volt. Let's say minimum 10 millivolt and maximum 10 volt. So that's the input. And at the output, we have Vout. As shown, this Vout, we want to see how the circuit is working in such a way that Vout can be equal to 1 minus log base 10 of input voltage, or Vn. So it's an interesting relationship across a wide range of input, say between 10 millivolt and 10 volt of input voltage. Output is equal to 1 minus log base 10 of Vn. That has a considerable practical application. So this is why it is referred to, this circuit is referred to as logarithmic amplifier or log amplifier. Let's see how this is working. Notice that the plus minus supply voltages are properly applied for both op-amp, so they are properly biased, both of them, op-amp let's say 1 and op-amp 2. At the same time, we have negative feedback. So intuitively, for example, just to notice, positive terminal of the first op-amp is grounded, so it's 0 volt. If, for instance, negative terminal, for whatever reason, start going up more than 0, then op-amp having a, let's say, very large open loop gain, immediately try to push the output to negative 12 volt roughly. As a result, it tries to basically pull down the emitter voltage, and it means trying to, as a result, increasing the base emitter voltage of this transistor, let's say T2, and which means it will increase the current of collector of that transistor. That is the same current here. So this current is going up as a result, and because that current is also passing through resistor R, then the voltage drop across resistor R is increasing, which means it is trying to reduce. Given that one side of this resistor is fixed at 10, with the voltage drop across resistor R VR increasing, then it means that the other node, which is the negative terminal, should drop. So you see, when it started, it was going up, but then the circuit is trying to bring it down, so counteracting. That is intuitive explanation why it's a negative feedback for the first op-amp. The second op-amp also the same way. Just to understand how the circuit is working, let's say the positive terminal is grounded, as you can see, for the second op-amp, so it's 0 volt. If for whatever reason the negative terminal, for instance, increasing suddenly, slightly, again because of very large open loop of op-amp gain, let's say gain, since negative terminal becomes larger than positive in this sort of intuitive discussion, then it tries to pull down the output voltage, or Vout, toward negative 12 volt. And as a result, when that is happening, because of this sort of a voltage division between R2 and R1, as a result, it is trying to pull down, let's say, this node as well. So Vout is going down, this node voltage is going down, VBE is basically affected. But the thing is, since 10R and 0 is fixed, it means this current is fixed. So base emitter voltage is fixed and defined by this 10 volt and R resistor. But since we are pulling down the base, it means we are pulling down the voltage of emitter. If we do that, since base of this transistor T1 is grounded at 0, by reducing the voltage of this common emitter, it means we are increasing the base emitter voltage of this transistor T1. That means we are increasing this current, which is the current of T1. And if we increase that current, if the circuit is increasing that current, that's the same current that is flowing this way. There is no other way for that current. So this is this current. And if that is increasing, it means the voltage drop across resistor R is increasing. And since Vin is fixed, it means as a result of this increase of voltage drop across resistor R, this node should, the voltage at this node should go down, which means again counteracting what it started. So we said at this node, initially somehow it's going up voltage of that node, but then you can see that the circuit is now effectively trying to bring it down. So intuitively we proved that. Also we have a negative feedback for op-amp number 2. And also this is a good way of discussing the operation of this circuit. Now let's write down the formulas and quickly find the relationship between the input and output of the circuit. Okay, so as a part of that, let's name the transistors as I just tried. So let's refer to this as BJT, or bipolar junction transistor T1, this one T2, and we have 0 volt at the base of T1. Op amps, of course, as mentioned, so op amps are properly biased, so op amps are in linear region of operation as a result of the negative feedback and proper bias. And therefore, virtual short is guaranteed by negative feedback. So voltage at positive and negative terminal is the same thing. So that's virtual short. So if we have 0 at positive terminal, for the reason I explained, we have 0 at negative terminal, which is virtual ground. And also for the other op amp, we have positive as at the positive or non-inverting terminal, and therefore we have 0 at the negative terminal as well. Okay, so we have 0 volt here. So it's easy to find this current, which is referred to as, let's say, I in. So I'm going to refer to it as I in. The same thing here. 10 volt is on one side of resistor R, and we also have, let's say, 0 here. So therefore, we can easily find the current that is going through, let's say, this resistor. All right, let's refer to it as simply I reference, IR. This is Vref, or voltage of reference voltage of 10 volt. We have also IRef, which I just in an abbreviation, I'm just saying IR. Now, this current IR can only go this way because in a steady state cap is open, so capacitor is not passing any current, and this current IR keeps going as a collector current for transistor T2. The current I in keeps going down as collector current for transistor T1. The most important thing to notice that these two bipolar junction transistors, as I mentioned earlier, are matched BJT transistor in the same package. For example, Analog Devices and also Texas Instruments and other providers, they have, for example, onsemi, they have a solution for either dual matched bipolar transistors or, let's say, quad matched bipolar transistors, so 2 or 4 transistors. We have to use those packages. You can find them in DigiKey or Mouser. So let's say these are perfectly matched transistors to a good extent, and as a result, whatever we have, let's say they have the same junction and transistor properties, so same beta or transistor current gain, which is collector, let's say, current to the base current. So that's the same for both transistor. And also when we have, let's say, same base emitter voltage for them, then we have the same current. Of course, here there is no indication that they necessarily have the same base emitter voltage. But let's refer to it as voltage of base for transistor 1 is 0. So voltage of base emitter 1, and then of course with this polarity we have voltage of base emitter 2. What matters to us is this node, basically voltage of base of transistor 2. Let's just write just the KVL or Kirchhoff voltage law like this between the VB2 and the VB1. So what I can say is this: VB2 minus VB1 is equal to voltage of base emitter transistor 2, so this drop, and then minus voltage of base emitter transistor 1, and so that's what I'm computing here. Okay, so what do I get? VB1 of course is 0, so that's connected to ground, as you can see here. So therefore what I can say is VB2 is equal to, now I'm going to use Shockley current voltage or voltage current of PN junction, let's say of the transistor, bipolar junction transistor, which says the voltage of base emitter is simply equal to, it is VT roughly, then a natural log of the current of collector or emitter divided by saturation current, and that is for transistor 2. So I have to write IC2. And then we have minus VT for this one here. So the first one I wrote is for this guy, and the second one for this guy, Vt again, natural log ln IC1, because it's VBE1, the base emitter of transistor 1 with respect to its collector current. So IC1 divided by IS. This is what is referred to as Shockley. So IV equation or VI equation of PN junction of bipolar transistor. Okay. The benefit of doing it this way, basically we have this sort of a connection between the transistors, is this IS or saturation current of transistor is very much exponentially depending on temperature. So we want to get rid of it. Otherwise, if we don't, then the result of this circuit will be very much temperature dependent. I'm going to talk about how we reduce temperature dependency for the outcome of this circuit as much as possible. Okay, so we do the subtraction of these two log, and the thermal voltage Vt is the same for the two transistors. So this is thermal voltage Vt. I'm going to just quickly refer to it. Vt is well known, Boltzmann constant, K times junction temperature. So this one, T, is the PN junction temperature, and then divide by Q. In room temperature, roughly, if the junction of these two transistors, which are on the same package as I mentioned, they are matched, if they supposed to have same junction temperature, if that is room temperature in Kelvin, that would be roughly about 290 degree Kelvin, roughly. Therefore, we can say with the values of, let's say, Boltzmann constant known and Q, which is the electron charge, then this is roughly Vt equal to, at room temperature, Vt or thermal voltage is roughly on the order of 25 millivolt, 25, 26. Okay, so that's the value of Vt nominal at PN junction room temperature. Therefore, I can say voltage of base of transistor 2 at this node, which is the very important node, because from there I can find V out, is equal to Vt natural log, and we have IC2 over IS divided by IC1 over IS. That's how this subtraction turned out to be in log form. And then IS cancel out because it is again both transistors in the same package matched, so they have the same saturation current. Then that's the best thing happening, because we get rid of the most dangerous parameter as a function of temperature, IS. So now it becomes Vt natural log of IC2 over IC1. Well, it's about time to replace these values with what we can compute here. So I'm going to write it here. I in simply is the voltage across R, which is, I in is this current, which is the current of collector of transistor 1, is equal to Vin minus 0, the two voltages across this on the two sides of resistor R. So it's basically Vn divided by R. So that's equation, let's say, 1. The same thing I can say about IR, reference current, same idea. On one side of resistor R, we have 10 volt. On the other side, we have 0 because of the virtual short and virtual ground of op-amp. So I can say IR is the voltage drop across R, which is basically 10 volt or reference voltage. So let's put it there. I'm going to just write Vref or VR divided by the value of resistor. Let's refer to this as equation number 2. Now we have equation 3 here, what we found. So what I'm going to do is I'm going to just substitute in equation 3 using equation 1 and 2, and I'm going to substitute for IC2 and IC1 values in equation 3. So voltage of base of transistor 2 here is equal to, so we have Vt natural log of, instead of IC2, I'm going to substitute from equation, that's the IC2, which is IR. See, the collector of transistor 2 is basically the reference current. So I'm going to use equation 2, and I'm going to just substitute VR over R. So let me put it here. So VR over R. And instead of IC1, you can see that it's current of collector of transistor T1. So it's I in, which is from equation 1, V in over R. So V in over R. These two R cancels out. I'm going to talk about how we select the value of R and what type of resistor it should be so that it become practically more accurate. So it become VT natural log reference voltage divided by input voltage. Great. So this is the value of voltage of base of transistor 2, and then we have equation 4. Now the benefit of that we have is if we properly select the value of R2 and R1 in such a way that the effective current, let me show it with different colors. So the effective current that is passing through the branch of R2 and R1 is much larger than the base current I base 2. So if we can neglect I base 2 by proper selection of R2 and R1, then we can assume that practically R2 and R1 are in series, and therefore from V out we just have a voltage division between R2 and R1 to get to V base 2. So if that is the case, I'm going to write it here. So let's assume R2 and R1 are small enough, meaning that the current passing through them, which I refer to as, let's say, I out, just for the sake of ease of reference, so are small enough so that I out, and I out meaning this current, is, so it's not exactly I out, but I'm just referring to it as I out name. I out is much, much bigger than, let's say, I base of transistor 2. Therefore, we can neglect I base of transistor 2, and I can say roughly the voltage of base of transistor 2 is just a voltage division between these two guys and V out, which then becomes R1 divided by R1 plus R2 times V out. And therefore, I can say V out is simply 1 plus R2 divided by R1 times V base 2. But then from equation 4, so I'm going to use equation 4, substituting for the voltage of base of transistor 2. So I get V out is 1 plus R2 over R1 times thermal voltage VT, which is roughly 25-26 millivolt, natural log of VR over Vn. Great. So that's the general formula. Let's now substitute for the value of these guys. So I'm going to just refer to this as equation 5. Okay, equation 5 is clearly showing that the output voltage of this circuit, if properly designed, then is related to or proportional to natural log or a natural logarithm of a ratio of VR over Vn. So we're almost there. Let's rewrite this. So I'm going to write as V out equal to 1 plus R2 over R1 times VT, let's keep it, but then I'm going to just write on top of it as a reference that this is a thermal voltage roughly 25 millivolt. 25-26 again. So times, instead of the ln, just obviously ln is log base E, whatever value. So instead of VR, I'm going to just write 10. 10 over Vn because the reference voltage is 10 volt. So I'm just making sure. So instead of ln, I'm just going to write log base E and then 10 volt divided by voltage at input, which is Vn. So now I can write, instead of log base E, I'm going to write log base 10 of 10 volt divided by voltage at input times log E, log 10 base E. So we know that the product of these two log, based on the log property, would be just equal to exactly this guy. But this value here, log 10 base E, is roughly 2.3. So it's a constant, obviously, this value. Now 2.3 times 25-26 millivolt is a well-known value, roughly about 60 millivolt. 56, 50, 57, 58 millivolt up to 60, depends on what we define as the room temperature. So with that, we can say roughly that from this equation we get, let's say, 58 millivolt times, so that 58 is 25 times 2.3 times 1 plus R2 over R1 times log base 10, 10, and instead of log base 10, I can write obviously log 10 volt base 10 minus log Vn base 10. I can write instead of this guy. All right, so what do I get now? I get, therefore, V out is equal to, so you can see I have 58 millivolt times 1 plus R2 over R1, and then times log 10, 10 is just 1, minus log V in base 10. So if I select R2 and R1 properly in such a way that it satisfies this requirement, so that's 1, and also it satisfies to that we can set this coefficient to 1, then I get exactly what we want. Because in this circuit I said prove that we have a proportional relationship between output voltage and input voltage like this. We already proved it. This is showing it. Now except that the problem says select the value of components such that we get exactly 1 minus log base 10. And to do that we need this coefficient here. So let me use a different color. We need this coefficient here to be equal to 1, roughly. So we set it to 1, and if we do so, we get 58 millivolt times 1 plus R2 over R1 set to 1, and we get roughly R2 over R1 equal to, let's say, 17.4-ish, 16.4-ish, roughly. And a good design choice would be setting so that values of resistors are practical and can be selected as discrete components, for example, would be if we set R2 equal to 3.3 kilo-ohm, which is a standard resistor, and R1 equal to, say, 200 ohm. These are standard resistors, so they're available. If we do so, the ratio between these guys is roughly matching the 16.4 requirement. And also the nice thing about that is R1 plus R2 then is equal to 3.5K. And what is the meaning of that? Well, the meaning of that is then the current I out, depending on what, for example, let's say value you're chasing. Let's say V out is 1 volt, for instance. If V out is 1 volt, so let me put it this way. I'm going to show you why this is a good choice. If with this sort of a relationship that we have, so if this, I'm going to highlight it with, say, a new color now. Okay, so let's use maybe blue color here. So this is the equation that I found. So in this equation, especially with this value set to 1, I get to let's say 1 minus log base 10 Vn. So what is the meaning of this? It means when Vn equal to max 10 volt, log 10 base 10 is 1, and 1 minus 1 is 0. So V out is roughly 0 volt. Let's say when Vn, remember that Vn is a voltage between 0 and 10 volts, so minimum 10 millivolt, for example, close to 0. So when Vin is 1 volt, I'm going to reduce Vin every time on a scale of 10. So when Vin is 1 volt, then V out, according to this equation, is log of 1 base 10, which is 0, and therefore 1 minus 0 give us 1 volt. And when Vn is 0.1 volt, which is 100 millivolt, then V out is roughly equal to, so is going to be equal to 1 minus log 0.1 base 10, which is minus 1, and 1 minus minus 1 is 1 plus 1, which is 2. So, and one more step. When V in is 10 millivolt or 0.01 volt, so 10 millivolt, then V out is 1 minus log base 10, 0.01, which means this is negative 2, and 1 minus minus 2 give us 3 volts. So see, every 10x reduction in the value of input voltage from the max 10 volt and lower, resulting in the output voltage with this equation going up from 0 volt minimum to 1 volt. So effectively we have, at the output, we have this relationship with input. So V out over V in is has a slope of roughly minus 1 volt per decade. By decade, I mean every 10x reduction, and especially given that it's minus 1, it means every 10x reduction of input voltage, we have 1 volt increase. So that is the meaning of that negative 1. And every 10x increase, let's say from 10 millivolt minimum, when output is 3 volt, when we jump by 10 times and output goes from 10 millivolt to 100 millivolt, then the input goes from 10 millivolt to 100 millivolt, then output goes from 3 to 1, 3 to 2 volt. So basically negative 1 volt change in output for 10x change, 10x voltage change at input. That's exactly the meaning of decade. Every 10x input voltage change resulting in negative 1 volt change at the output. So given this sort of outcome, when, for example, we have 1 volt at the output, so if V out is 1 volt, for instance, then the current at the output that we defined as I out, meaning this current, the current that is flowing downward, so the current that is flowing downward, is roughly equal to 1 volt divided by, say, 3.5 kilo ohm, the sum of R1 plus R2. So I mean the sum of these two guys, because it's V out and 0 or ground on the other side of them. So therefore, what I can say is, is 1 over 3.5 kilo ohm, or let's put it this way, 1 over R1 plus R2, which is 1 volt over 3.5 kilo ohm. And this is roughly, I think, 280, if I remember correctly, 285 or 86 microamp, about so. So this is considerably larger than the current of the base, because, for example, for the 1 volt scenario, we are having V in 1 volt. So when output is V out 1 volt, input is 1 volt as well. So let me go back up. If V in is 1 volt, then I in is 1 volt divided by resistor R. For example, if we set as a part of design, if we set the value of resistor R, let's say equal to, let's say 2 kilo ohm. So let's set all these resistors R 2 kilo ohm. So we have 3 resistor R in the circuit. I'm going to set them to 2 kilo ohm. As a result, when V in is 1 volt, we get I in 1 volt over 2 kilo ohm, which means 500 microamp, 0.5 milliamp. With the beta of these transistors easily on the order of 200 or 300, so the current over here, the current gain of transistors, these bipolar junction transistors, 200 minimum to 300, 400, at the 500 microamp, which is the collector current range for these guys, we have the base, let's say at sort of order of 200 less than what you expect to see. This one is, for example, injecting 5 milliamp here. So we get, let's say, 50 microamp at the base. And while we are having, let's say, on the order of, 25 microamp, because beta is at least 200. So IR is 5 milliamp, because it's 10 volt divided by 2 kilo ohm, and therefore you're talking about, say, 5 milliamp. But then with the beta of at least 200, you get 25 microamp here at the base, current of the base, and that is 10 times, more than 10 times less than what I refer to as 286 microamp. So all I'm saying is we have the degree of freedom to select R2 and R1 properly so that the current through these guys is practically much more than 225 microamp, the current of base of transistor T2. So in practice, what happens is when we are at max 10 volt Vin, output might not be exactly 0 and might be on the order of 30 to 40 millivolt, which is good enough for us. So it's not about the accuracy of the output at this level, but what matters is as input is reduced and as current is dropping, we get to relatively more accuracy for output in terms of 1 volt, 2 volt, and 3 volt, and so on and so forth. Now, the last thing I would like to mention is the choice of resistors. So let's say 2 kilo ohm is the one you want, or 5 kilo ohm for all these resistors. My recommendation is we use thin film. So thin film resistors that are the ones with, so these resistors, let me just make sure that we have enough space to talk about this guy. I'm going to remove these guys to here. Okay, now the thin film resistor, so the thin film resistor, the good thing about that is, let me just get rid of this. They have an accuracy of 0. Let's say you have the option of purchasing them with the accuracy of 0.01%. So if it is, for instance, 2 kilo ohm, or let's say 0.05%, so it depends on what you purchase. But basically it means the variability or variation of the value of these resistors are pretty much close to just one ohm or less. So there could be, you can guarantee a very good matching between these resistors, so that when we are canceling them out in this equation here, see, let me change the color so that you can see the equation. In this equation, that we canceled out the two, let's say, the two resistors in denominator, we assume they are exactly equal, which what I'm trying to say is practically with the proper selection of resistor like thin film resistor, we can guarantee that they are practically very close to each other. So that's what I'm trying to make sure practically we have in mind. Now, the other practical consideration is this R1 here can be selected to be, for example, a TEMCO or temperature compensated resistor, or similar type of resistor with, let's say, positive temperature coefficient. So let's say it's sort of a standard TEMCO resistor has a positive temperature coefficient of on the order of, say, 0.035, I think, if I recall correctly, percent. Or so what I'm trying to say is we can select this guy in such a way with positive temperature coefficient so that its effect in there you go, it shows up in R1 in equation, in this equation. You can see that it is showing actually in denominator, while we have VT in numerator. So VT has a negative temperature coefficient. So VT has a negative temperature coefficient, and you can see that this negative temperature coefficient can be cancelled out with, so let me just put it there. Okay. What happens is, as temperature increasing, let's say, sorry, VT as positive 1 because VT is KT over Q. So as temperature is increasing, VT is increasing. So we need to have something that counteract that, and that would be R1. So if VT has a positive temperature coefficient, because it is obviously KT over Q as I'm showing here, so as temperature is going up, VT is going up. So that means positive temperature coefficient. Then R1 also with proper temperature positive coefficient would cancel out the impact of VT numerator and denominator. So effectively we sort of minimize even the impact of VT's sensitivity to temperature using R1 if R1 is selected properly. I hope that this example is helpful in terms of showing how a logarithmic amplifier practical design can be analyzed and designed, and the value of components can be selected in such a way that we realize this simple relationship between output and input for a wide dynamic range or wide range of voltage from, let's say, 10 millivolt to 10 volt for this circuit. Of course, the lower level, whether it's 10 millivolt or 1 millivolt, depends on the minimum IC current for these matched bipolar junction transistors. So if lower IC current or collector current is acceptable for these matched bipolar junction transistors, then we can go even lower towards 0, like 10, instead of minimum 10 millivolt, we can go to minimum 1 millivolt. It's possible to realize, let's say, 5 decades of a scale or range down to, say, 0.1 millivolt with this circuit with the proper design. I hope this example is helpful. Thanks for watching.